So now that we have a better understanding of what vector fields are, what they look like, how do we understand their integral curves, the parameterized curves that follow the vector field's arrows, now the next question is, what do gradients of scalar valued functions have to do with any of this? And in our previous example, the one that we just finished working on, we had this great example of a vector field where it just so happened that we found a scalar valued function x squared plus y squared whose gradients were perpendicular to our original vector field at every point. And because they were perpendicular at every point, it meant that the integral curves of our original vector field are going to follow the contours of this function whose gradients are perpendicular to our original vector field. And so that was just a really happy, I won't call it a happy accident. It's not a coincidence, but it's when we can find such a scalar valued function whose gradient is perpendicular to our vector field, then we know for sure that the integral curves of our vector field are going to follow the contours of that function. In this case, the contours of that function were just circles centered at the origin. And so if we look at that another way here, let me get... So here is the vector field xi plus yj, right, which was the gradient of the function x squared plus y squared. And if on top of this I superimpose the contours of x squared plus y squared, you'll notice that there's a relationship between the gradients of a scalar valued function and the contours of that scalar valued function. This is a relationship that we've already seen back in chapter 10 when we first met the gradient of a function. And so we can use this relationship between gradient and contours as a way to help us to get a different perspective on where gradient vector fields can come from. So the next activity that we're going to work on here is going to ask us to start with these three sketches of contour plots of functions. And we're not given the formulas for these functions. So we have to do this just by using our conceptual reasoning powers. And part A asks us to sketch on top of these figures what the gradient vector field of the function whose contours are plotted would look like. Right? So pick a few places and sketch where the gradient vectors should be pointing. And notice in these contour plots that they're also labeled with their heights. They're kind of small little numbers, but you should be able to read them, I hope. So that can show you where the function is getting bigger, where the function is getting smaller, and so forth. So there's three different contour plots. Your job is to, on each of them, sketch a few gradient vectors that, first of all, their directions should be as accurate as you can manage. And also, try to get a sense of their magnitudes a little bit. Like, are there places where the gradient vectors are going to be larger in magnitude? Are there places where it's going to be smaller in magnitude? So, you sketched in some gradient vectors that correspond to these contour plots, and you used kind of two important principles to do that. The first is that the gradient vector always points in the direction of greatest increase, of most quick increase of the function. And so that direction is always perpendicular to the contours of our function, because the contours are the directions along which the function increases not at all. And so if I want to increase as quickly as possible, I need to get away from my contour as quickly as possible. So I need to move perpendicular to my contour. And you use the heights on these contours to determine which direction was increase and which direction was decrease. And you made sure that your vectors pointed in the increase direction in each case. The second principle was that the magnitude of the gradient vector tells us the largest directional derivative that the function has at that point. Because after all, the directional derivative is just a dot product of the gradient with a unit vector in the direction that we're asking about. And so that directional derivative is maximized when the direction that we're moving in is parallel to the gradient, because then the cosine of theta is equal to 1, which is the largest value that the cosine can take on. And so what this forces us to do is to wrestle, which is what we spent, I think, the most of your time doing on this activity, with how a contour plot gives us information about how steep the graph of a function is. So where the contours are close together, like they are up here, for example, where the contours are close together and my contours are equally spaced apart in z values, which these ones are, so these are equally spaced apart by 25s. Right? So if I want to get 25 points higher on the z-axis, then where the contours are close together, I don't need to change x and y as much to get an increase of 25 in z to get to my next contour. And so the denominator in my directional derivative would be small to get a change of 25, for example, in my numerator. And so when the denominator is small, it makes the fraction large. So the directional derivative is large. The largest directional derivative is large where my contours are close together. Where my contours are not close together, in order to get 25 points higher on the z-axis, I have to change x and y more. I have to walk further on the map to change my elevation by 25 feet, right? And so over here, the largest directional derivative is smaller because I have to walk further to get to the next contour, so my denominator is larger in my directional derivative, and so the directional derivative is smaller. So wide spaces between contours means very short gradient vectors. Close together contours means very long gradient vectors. And always those gradient vectors are perpendicular to the contours, as in each of these three examples that you just sketched. So what comes next? I think this was the challenging part, because now we get to do some things that are more computational in nature. So the next set of questions are about how can we tell if somebody just comes up to me on the street, because it happens to me all the time, and hands me a vector field. How might I know that that vector field is a gradient vector field? Right? How could I know that it's going to have those properties that gradient vector fields are going to have? And so these next couple of parts B and C, hand us a vector field, 6xy, 3x squared plus 9 radical y. And they ask us to verify, first of all, that this actually is a gradient vector field by trying to find a function, little f, such that the gradient of little f is equal to this vector field. That scalar function that we get in the process is called a potential function, sometimes called a scalar potential function, because it's a scalar function, scalar valued function of several variables. Its gradient is a vector field, and we hope that its gradient is going to be this vector field that's in this problem. So you'll try to find such a potential function for the example in part B, and then in part C, you'll think a little bit about, well, is this the only option, or could there have been other scalar functions that also have as their gradient this vector field in this problem? So we'll do parts B and C. And then when it comes to part D, I have a few extra follow-up questions to this one, so I've augmented this activity a little bit. So let's do B and C for now, and then we'll do D after we've had a chance to decompress from those two. So when you took an antiderivative of this function with respect to x, you got one answer, right? That our function, it could be 3x squared y. When you took the antiderivative of the y component with respect to the y variable, you got a different answer. So the question is, can we have a single scalar value potential function whose x partial derivative gives us the right thing and whose y partial derivative also gives us the right thing? So can we make these two agree with one another? So which one is a potential function for f?
The second one, right? Because if you partially differentiate with respect to x, you get the 6xy, which is what you want for the x component. But then if you partially differentiate with y, you get the y component. So looks like the second one is pretty good.
The second one looks like it should work,
Mm-hmm.
because as you say, when you take the y partial derivative of this second example, the first term here, 3x squared y, turns into, wait a minute, sorry, the x partial derivative gives me 6xy, so that works. And the y partial derivative gives me 3x squared plus 9 square root of y, so that seems to work. So let me ask this. So what did this first try miss? And why did it miss it? So anytime we take antiderivatives, right, indefinite integrals, we always have this ambiguity, right, that when you take, and when we're looking for the antiderivatives of a given function, those antiderivatives can differ by a constant. The problem is that our antiderivative that we took in this first example was an antiderivative with respect to x. And so it treated the other variable, the y variable, as though it were a constant. So the constant that we get as part of this antiderivative is not necessarily strictly a constant. It could be a constant which depends on y. Constant which might depend on y, because we treated y like a constant in the process of taking an antiderivative where x was the variable, right? This is the game that we play when we do partial differentiation. And then the same thing is true when we took the antiderivative here with respect to y. We could have also had a constant here, And that constant might depend on x. So sometimes what you'll see authors doing in this process is that they'll write plus c, but then they'll write it so that c looks like it's a function of whatever was the constant variable or variables in the process of finding that antiderivative. And so if I do that, then I can sort of see how this first try, right, this first antiderivative, can be matched up with the second antiderivative just by identifying, oh, this constant function of y is probably just 6y to the power 3/2. Right? So that piece is just that piece. And that's how we can reconcile the two of those things. And so there is an example of a potential function that we could have gotten for this vector field. So this vector field is a gradient vector field because we just found a scalar function called the scalar potential function for this vector field, such that if I take the gradient of f, I get exactly the vector field that we were looking for. Okay, so let's move on to part C real quick. Could there have been another choice that we could make? Is there another function that has as its gradient this vector field? All right, great. So you figured out that adding just an arbitrary constant, a true constant that depends on neither x nor y, is also going to give us a scalar potential function, right? This is when you take a physics class and you think about energy as being one of these classic examples of the kinds of functions that you deal with in physics, that the potential energy of a given system, right, doesn't actually depend on, like, the actual number that you get out of a potential energy function is not that interesting, right? It's not interesting to say, oh, the potential energy of this system is 150 kilojoules or something. What's actually materially important is how potential energy changes. The gradient of potential energy is what's important and not the values themselves. And that's because potential energy is really just measures all that we can do with potential energy is convert it into kinetic, basically. We can get energy out of it based on how the potential energy surface slopes and changes. And so just adding a constant to a potential energy function gives us all the same dynamics of the system as the original potential energy function did. So all that is to say that when we find a scalar potential function for a gradient vector field, we can always just add a true constant or subtract a true constant into it and still get another scalar potential function. Just like the process of taking any indefinite integral or antiderivative in calculus. Adding a constant is always going to be invisible because the derivative of that constant is always just going to get washed away to zero when we find even the partial derivatives are going to do that as well. So the next place we'll go is to see if we can develop some criteria. If somebody hands us a vector field, how can we tell whether or not this vector field is a gradient or not? And so in part D, I think what the interpretation, ungradient, I like that. It's like the anti-gradient. I have a vector field and I want to find something of which it is the gradient. So we're anti-gradienting the vector field that we started with. So let's try that with this vector field in part D. Using antiderivatives, see if we can find a scalar potential function for this f. And then in parts E and F, we're going to develop a different kind of test to see whether or not something has a chance at being a gradient vector field or not. But let's just use the standard ungradient approach in part D, and then we'll look at a couple of extra bonus methods after that. So yeah, try as we might for this example. If we take the antiderivative of the x component with respect to x, we get 3x squared y plus something which might depend on y only. And then if we take the antiderivative of the y component with respect to y, we get 2xy plus 6y to the 3/2 plus something which can depend on x only. And both of these terms that have x's and y's in them aren't accounted for in the other version of this antiderivative. So there's no way to match up the 3yx squared with some constant that depends only on x, for example, or vice versa for the 2xy. We can't match that up with a constant that depends on y only. So there is no way to reconcile these two. It apparently is not possible to reconcile these two versions of the potential antiderivative. I guess I'm using the word potential here as a double entendre, right? A possible antiderivative that would be called a scalar potential function, but one appears not to exist in this example. And this is where the authors of this activity sort of leave us in a lurch, right? And just like, okay, let's just move on. But I wanted to add a couple of extra parts on here so that we can have a little bit more assurance of how do we know that it's literally impossible for us to match up these two versions of the antiderivative. And so instead of reaching for the ungradient process, and gradient is a normal vector to the contours of a function, instead of reaching for the ungradient process, let's see if we can develop a way to use derivatives rather than antiderivatives to test for whether it's even possible for a vector field that's given to us is a gradient. And so to do that, my reminder to you in part E is that if I have a function g that has continuous second-order partial derivatives, then the mixed partial derivatives, the xy and the yx second partial derivatives, are equal to one another. So if we take the x partial and then the y partial, we get the same function as if we took the y partial and then the x partial. And so the first question is, what does that tell us about the components of a gradient vector field? So if I have a vector field that I know is a gradient, and its components are called p and q, then what does this second-order partial derivative equality tell me about the functions p and q? And then that's going to give us a way to redo part D to test this vector field for whether it might be the gradient of something, but using derivatives of its components rather than trying to take antiderivatives of its components. So that's how we'll wrap this up in parts E and F. So you figured out that in order for a vector field that we're handed, if it has components p and q, in order for it to be a gradient vector field, it is necessary that the y partial derivative of the p component, the first component, and the x partial derivative of the q component have to be the same as one another. dp dy has to equal dq dx. This sometimes gets a name. We call this the screening test for whether a vector field may be a gradient of some potential function. Right? So instead of trying to take antiderivatives and see if they match up, just test the y partial of the x component and the x partial of the y component and see if those two things agree with one another. So again, why is this working? Like, what are we actually trying to do here? So we're given a vector field. We know its x component. We know its y component. We want to figure out if it's even possible for there to be a scalar function of which this is the gradient. In other words, one function whose x partial is this and whose y partial is that. And so to figure out if that's possible, we take the y partial of that and the x partial of this, and we compute them. In this case, if we do that, we get 6x and we get 2. And since those two things don't agree with one another on the one hand, on the other hand, those things are the two mixed partial derivatives of f, right? This one is the y partial of the x partial. This one is the x partial of the y partial. And so as long as f is a function with continuous second-order partial derivatives, we would need for those two to be the same as one another. But since they're not, since we don't have equality, since these mixed partials are different, there is no such potential function that's possible, or at least no such potential function that has continuous second-order partial derivatives with continuous second partials. And since these second partial derivatives that we wrote down here are continuous, that rules out this possibility. Right? So this gets called the screening test. Just check the y partial of the x component and the x partial of the y component. Those two things need to be equal to one another if our vector field is the gradient of some scalar potential function.